Yeah, welcome back everybody to the second session. We have two talks in this session, and the first talk will be given by Frank Lechermann, who's going to tell us about the superconducting Nickelates.
Yes, yeah, thank you for the introduction. So welcome again to this second talk of mine. So now this is the scientific talk of the current research that we are partly pursuing at this moment. So as you will see, it builds a bit up on this, what we did yesterday, this tutorial on DMFT. So this kind of presentation will be kind of an approach, application of the things that we learned yesterday. Of course, at a bit on an advanced level, but I hope you can still recover some things that you have seen yesterday, and I will try to make a bit connection when possible. So this is about superconducting Nickelates. And before introducing the topic, let me first also acknowledge my collaborators. So this is work that has been partly done in Hamburg and in Bochum. So in Bochum, there's Steffen Bötzel, Yannick Gondorf, and Ilya Arimin. So this is a picture of Bochum University that helped a lot in recent years to do advanced work on this. And there was additional support, especially in the low energy physics, that we tackled from Brian Anderson's group with Andreas Kreisel, Astrid Römer, and then additional help when we want to go beyond DMFT. So we have learned a little bit yesterday that there are also techniques to go beyond DMFT to bring in non-local physics. And there we got great help from Zhenya Stepanov, Matteo Vandelli, and also some Sascha Lichtenstein in Hamburg. So what is the topic about? So it's, as it said in the title, it's about superconducting Nickelates. So this is a topic that emerged about 5 years or so in the field, that it was long pursued, that one can find additional unconventional superconductivity beyond cuprates in other systems, and namely Nickelates. So there are two classes of families that have been found. So these are these two kinds of superconducting Nickelates, which is already a bit different from cuprates, if most of you maybe know. So let me very quickly characterize these two classes of families. So the first one I just found at the early stage at 2019 in Harold Wong's group in Stanford by Danfeng Li, were these thin films of 3D 9-ish like infinite layer Nickelates on a substrate of on STO. And if you dope them with some strontium content, you get a TC of about 10 to 20K. And some years afterwards, there was the group of Julia Mundy in Boston. They found a similar kind of superconductivity in layered systems of same kind of structuring of infinite layer kind of type. I will make the connection then in a few minutes of neodymium 6, nickel 5, oxygen 12. And also TC is about 10K, but you see that the TC is really very blurred out and goes more or less down to zero how you will define it. So that is a bit a tricky case, but still superconductivity was confirmed in this system also. And then there have been last year the finding from the Chinese group of Meng Wang, new kind of superconducting Nickelates, which then are really so to say high TC, which goes up to 80K at least reported, but under high pressure. So there's always a caveat with this Nickelates that even have to bring it in thin films or in some specific layering on a substrate, or in this case in a high pressure regime. So these are these bilayer systems, lanthanum 3, nickel 207, even without doping also, and also these 4-3-10 compounds, similar kind of structuring also under high pressure, but now 3 nickel layers, whereas you have two nickel layers here. And that was just, I think, published in Nature this year, but it was already found and reported on the archive last year in fall. And those usually go with occupation of nickel or 3D8-ish plus minus something. So these are already two kind of charging states. That's already interesting, and maybe there's a connection, maybe not. And it's already surprising because, as you know, in cuprates, which are some kind of the family member, as you would say, to this oxide superconductivity, we always have one kind of charging state like 3D 9-ish. But I will try to connect it a bit. So before going into these more complicated systems and trying to get some physics out of this, let me try to connect it, of course, as I already tried, to the cuprates. So I will not now fully remember things about cuprates because this is a large field, and I think most of you are already kind of familiar with that physics. So there's a phase diagram, as you know, stemming from the early days of 1986, where it was found that there is a 3D 9 system as the geometry, and there's an endothermic order, and you dope it with some holes, and then you reach the superconducting dome with a TC easily above 100K in newer systems. And the basic minimal model to get physics out of this, which well, it's still debated, but it is believed that is maybe sufficient. It's a one-band model of x minus y square kind of copper orbital, strongly hybridized with oxygen, giving rise to this Sangrai singlet. So Sangrai singlet means that oxygen and oxygen 2p and copper x minus y square go together hand in hand and form a low energy quasi-particle, which then should govern the main physics in this phase diagram. But you should remember that this one orbital like Sangrai singlet is not a simple atomic orbital, but it's a really extended one-year orbital. So there are, of course, a lot of discussions going if we need more degrees of freedom, explicit oxygen degrees of freedom or not. But again, I will not go into detail of cuprate physics at this point. But there was a long-going idea that you could connect this cuprate physics to other systems, namely Nickelates, which are just close by, of course, in the periodic system. But there are some complications to this because nickel 2+, which is the beloved oxidation state of nickel, is 3d8. So it's not 3d9, and so you don't have easily a one-band system at the Fermi level, but usually two bands, as we will also discuss quickly. Additionally, doping nickelates, even if you reach a kind of mod insulating state that you also have in the cuprates, is quite different because you don't easily get a metal when you dope this system, but more quickly you get like in-gap state or boron physics or charge order physics or trapped states. So it's not always that simple that you have a mod insulator and you dope it and you get easily a metal out of it, as we also did yesterday in this simple task. Of course, in simple theory, it happens easily, but in reality, not, because when you actually dope the system, you have to bring in charge carriers, and it's not so clear that they easily hop just from mod insulator. We will also come back to this in a minute. So therefore, it was not easy to reach that scenario of cuprates in nickelates, and it was a long-going research. But then it was eventually found as reported, and we want to understand this, of course. Before we go into these more complicated systems, then let's maybe just get a very basic idea of nickelates in general. So what are the key systems that have been known for a long time, and how do they connect to this more specialized system where we now find superconductivity? So first, it's good to know what are the key frontier orbitals in nickelates, in oxides, because they are at the end of the transition metal row, and you know there's the 3D shell, and the dominant electronic physics happens in the 3D shell, but the 3D shell is nearly filled, yeah, of course, because they're at the end of the row. So they have usually 3D8, 3D9 configuration. So the dominant orbitals are then from the 3D shell, usually these two degenerate orbitals of EG kind. So it's dz square and the x square minus y square. And those two orbitals really play the main game in this physics. So this is important to know. That's usually a twofold orbital sector that is most relevant. And then there are key systems in nickelates which derive from this so-called Ramanujan-Popper series, where you have a different kind of layerings. Yeah? So starting from layering n equal 1, where we have the 2-1-4 system, yeah, which is the so-called cuprate analogon to the lanthanum 2 copper or 4. Yeah? You can see that here, that is a mod insulator or mod charge transfer insulator, also for the nickelates, but the gap is much larger as in cuprates, it's about 4 eV. And at the very end of this Ramanujan-Popper series, you have this infinite layer system, so to say, lanthanum nickel 3, which is a pure perovskite, which is then a metal, well, quite good metal, a normal standard metal, but it would be normally account for an occupation. If you do the counting of oxygen 2-, lanthanum 3+, it would be nickel 3+, where this would be nickel 2+. But you see, it's not really nickel 2+, because it's still 8 electrons in the calculations. It's still nickel 2+ from the calculation. That means that we have a ligand hole in the system. So that is a general result for nickelates. The nickel doesn't go very easily in oxidation state below 2+ or below, let's say, D8 occupation. Even if you normally have D7, it usually turns out that there's a ligand hole, meaning that the hole is not on oxygen, on the nickel anymore, but it's transferred to the oxygen. And that happens here, that you have some ligand hole physics, whereas here you have, it's a bit higher than 8 here in this calculation, but it's normally also 8. Yeah? But you have these two limiting cases where you have a very good metal and a good mod insulator. So those are well characterized and known for a long system, but still a bit kind of boring, of course, not super fancy. But actually, as we have just seen in the introductory slide, something happens in between, obviously, where we can reach superconductivity out of that. And to acknowledge this a bit clearer, we have to learn or tackle again this issue of charge transfer and Mount Hubbard physics. It was already mentioned in a talk this week, which I think is very important. And since it's so important also in this field, let me do it again here and put my finger on that. So the issue is that you have a large charge transfer, so splitting the oxygen band and the D band, and then crank up the interaction U. The interaction U is usually the smaller scale. So it means that you have Hubbard bands that we have talked about yesterday in an insulating kind of scenario that are split by the U, but the oxygen P band is more or less just a spectator. It's far away from all the physics, and we can concentrate on the Mount Hubbard kind of physics. So this is then also in an insulating regime, the Mount Hubbard insulator. However, when this charge transfer energy is rather small, so when the D band and oxygen band come rather close already without interaction, then cranking up the U means that the U is usually then larger, and the Hubbard bands are now split to such an extent that the oxygen is just in between. So oxygen then takes on a much more important role, a much more prominent role in all this interaction physics, and we have to think much more deeply and much more carefully about the role of oxygens in such systems. And the issue is that this kind of scenario of charge transfer physics, which is then playing a key role, is just coming very important at the end of this transition metal row, as you can see here in this plot. So this is former 3D_n, meaning the nominal deoccupation, which would be 3D8 for Nickelates, and so on. So if you look for these monooxides, which is all 2+, you see that this is like the D band, and this would be the oxygen kind of band, and they come closer, well, meaning that the charge transfer becomes smaller, and we're more in this regime towards the end of the row. For this nominal formal n-1, which would be then for nickel 3d7 formally, it's even more dramatic, and you see that the charge transfer really becomes very small at the end of the row. And just going back to the values we had in the calculation, so the charge transfer is small for lanthanum nickel 3, so this corresponds to this plot of 3d7 like that we have seen in other slides, so very small, where it's quite larger for the other system of 3d8 kind, which is the one above, and this would be the one below. So that matches more or less this scheme that we see in this trending pictures. Yeah? So the charge transfer energy is still high in these Nickelates generally of this Ramanujan proper kind. So let's move on now to the concrete system. First tackle this infinite layer system that have been found first from the Stanford group and then continuing also Mariando's group and so on. So there's been a long story that people thought very early on to characterize this infinite layer. So what means infinite layer in this case? It means something specific, namely that you take out the apical oxygen in your octahedron that would form around the transition metal site. And if you take out the apical oxygen, then you get formally this 3d9 state that you look for to have it resembling the cuprates. That can be done by bringing in hydrogen. Hydrogen pulls out this apical oxygen, and you reach this oxidation state 1, and after some chemical procedure. This was already found in the 80s, so very early on, but the characterization is very complicated. So it's not an antiferromagnetic insulator at stoichiometry as in the cuprates, so that's already more complicated. It has a strongly enhanced susceptibility, Curie-Weiss-like susceptibility, but doesn't order, at least not statically easily seen. Then there have been calculations very early on in the middle of the 90s from some French-Russian group that already claimed that this lanthanum nickel O2, which is then this infinite layer without the apical oxygen, is kind 3d9, but it's not an easy metal, it's not an easy insulator, so very hard to characterize. Then continuing calculation by Anisimov's group from Russia, Ekaterinburg, and also from Warren Pickett's group in the US, made that more clear. It has an X square minus Y square like dispersion, yeah, that you can see here. But there are some additional bands touching the Fermi level, this kind of self-doping pocket bands, which maybe complicates the picture different from cuprate again, where you don't have those states. And also here, it was mentioned by Warren Pickett's group that there might be even other orbitals, namely this Z square orbital, not only the X minus Y square orbital, but the second orbital that we've talked about is also important for the Fermi level physics. Okay, but then finally it was found. So as said, I will not talk a lot about this experimental characterization because due to the lack of time, but we can discuss afterwards if you're interested more. So this has been found. There's an resistive upturn in the stoichiometric compound. So it's weakly metallic, but not a super metal, not a super insulator, just as it has been characterized before from theory, so that fits. And then, as we said, with strontium doping of about 20%, you get a superconducting. And again, okay, it's a thin, it's a thin film on an STO substrate, and it's very hard to grow this stuff. So I could, well, not me, but some other people could talk like for hours how complicated it is to grow this thing. So that is very tricky. Yeah, that cuprates. People tell me that you can bake it in an oven like anyone can do that. I don't know, but anyway, but Nickelates are very, very tough. So only a few groups can do that because of various complications that I don't have time to talk about. So it's a complicated system. Therefore the progress is rather slow by experimental means, which has benefits and drawbacks concerning theory, as you may realize. So what's the phase diagram then? So that, of course, has then been mapped out by time. So this is the phase diagram of superconductivity for this infinite layer neodymium 3D9-like system. And that is a comparing phase diagram from cuprates. So it looks quite similar. No, there's a kind of a dome happening. You have sandwiching regime. The dome is not so far off concerning the different kind of doping. That is nice, but first of all, finding a dome itself, at least to me, is not so fancy, because I'm a simple guy. So what goes up has to come down in some point. So finding a dome is, I think, for me, quite natural to find at some point. But still, what I find more interesting is these sandwiching regimes, which are a bit different in these two systems. So as you know, in the high doping regime of cuprates, we find a very nice metal, even a nice Fermi liquid. And even with some finite doping, we find this pseudogap-like phase, but which is still metallic-like, not too bad. Whereas in the Nickelates, it's quite different. We find in the newer samples, it is not so weakly insulating in days. It's metallic-like, but not a very nice Fermi liquid. And especially in this low doping regime, it's very much insulating. It's called weakly insulating, but if you look at the data, well, there's not so much data there anyway, but it's very, the resistivity is very large, even in newer samples that have been done. There's more or less most goods, even the normal state conductivity in the regime where the superconductor appears there, which is in the end also not so surprising, because I just told you in the beginning that doping Nickelates is a hard job to do. It's not that you come up easily with a metal just by doping that, and it will become clear why it's that the case. Then, of course, you can look in Hall transport and further measures of transport, which has been done then quickly afterwards. And there could be a basic picture of two-band-like scenarios happening, whereas it's not clear what these two bands mean. It's just like a fitting procedure, but still there are kind of two relevant degrees of freedom that govern this phase diagram from experimental fitting procedures. Sure. Yes. What does this mean? Well, okay, I cannot tell by heart, but I think it's more or less just characterizing a kind of still wellish kind of conductivity, I would say, for my simple. I would have to look it up from the experiment. I cannot easily tell. But I would say that this is really, really more strongly insulating, where this has some reasonable conductivity, where you can find something. Yeah, that's a good question. I think that has not been mapped out completely, as to my knowledge. I cannot recall easily. Yeah, we have to look it up. Yeah, but that's a good question. But yeah. So there are different transport regimes that I can also talk about. So there is a kind of if you go up, especially in the superconducting region, if you go up to higher temperatures, then you have again kind of linear in T transport, like in the cuprates. So that is similar. Whereas here the transport is very, well, hard to characterize, I would say. Okay, let's then move on to theory, because of that is the field that I can maybe say a bit more, hopefully. So there have been put forward various kind of concepts, of course, to explain this kind of physics as has been seen. And I cannot go in very super detail into all of this, but just let me mention a few the directions that people followed after these initial findings. And the first one, of course, as I said already, is that is mainly x squared minus y squared driven. That is mainly cuprate-like physics that you just see in a different kind of flavorish sense. That is the main streamline of research, and it's also that most people still favor these days, I would say. Then there have been some people, especially like Fu Zhengzhang from China, that favor Kondo-like physics. I've talked about this resistivity upturn, that's the geometry, so that you could think of a condo-like feature. Yeah, remember we have these self-doping bands and we have this x minus y square. So this could both together form a condo-like scenario. That is what people follow in that direction. Then there's been, of course, thoughts about the issue of that we have these thin films on a substrate, that there might be interface physics very important, and this is still ongoing research. A part of it has been resolved. That is not a 2-deck, at least not in this original system that has been formed, but there's some kind of other reconstruction. But of course, the interface has still some importance, and that has still to be further analyzed if there are more physics coming up from the interface. And then, of course, there's a group which thinks that this is a bit of a different kind of superconductivity. It's not really x minus y square only driven, but there's these full 2 orbitals that we've seen. So dz squared and x minus y square are both in some way important to govern the superconductivity. And I think that's also where I more or less belong to at this stage. But let's then focus first on the density functional theory picture, because we know DFT is not perfect, but it's still a well-converged theory and gives us some good starting point, and we should agree on DFT picture because, as we said, that it's more or less well-defined in a given sense. So if we compare that between this kind of stoichiometric neodymium Nickelate and corresponding infinite layer cuprate, which also exists, is also superconducting, then of course we see some clear differences. First of all, there's x minus y square character. This is this orange character here. Dominant, of course, in cuprates, and there's nothing else much there. There's a bit of a copper dz square character, but it's well below the Fermi level and doesn't pop up towards the low energy. Whereas in Nickelates, it's always a bit more complicated. There is this x minus y square dispersion. We already talked about this. We have these additional pocket bands, these self-doping bands, yeah, that appear there, and they mix in already some nickel dz square character, as you should see in these fat band plots. And secondly, there is also, again, this nickel dz square below, but it's a bit closer already compared to the cuprate case. Yeah? So the nickel dz square is already, from pure DFT point of view, already a bit more relevant, let's say, mixing in towards low energy. Still, x minus y seems dominant, but still there's this kind of differentiation. The question is this relevant for the superconductivity or not, especially with doping, of course. A second very important feature is now these charge transfer energies, which I really want to highlight here, which I think is important and is a bit put under the rock in some other examinations of the systems. So we just talked about that in the Nickelates, you have a high charge transfer energy, and this is seen even, so remember we had for the lanthanum nickel 3, we had about 2 eV, for the 214 we had about 4 eV, and now it's even higher, no? Because it goes higher, 3D9 is even a higher charge transfer energy, about a 5 eV. Whereas in the cuprates, we have a very small charge transfer here, as surely most of you know, it's about 1.5 eV. So what I want to say with this is that if you think that this is very cuprate-like physics, it might still be, but it would be very surprising because the charge transfer energy in this Nickelates is not going towards cuprate physics, but it's just going the other way. It's just going up, it's not going down with this superconducting Nickelates. And I think this is an important feature, and it's a high energy scale, which really, if the physics would be very similar, could be, but at least to me it would be quite surprising, and because of this different energy scale. So now what we do beyond DFT, of course we do now what I said yesterday, so we now do the combination of DFT with dynamic mean field theory. So again, I cannot go in super detail on this, but the bottom line is this simplistic like picture that you take the DFT calculation, start from this, and then you single out a certain correlated subspace where you think that strong correlations are most important. In our case, that would be these nickel 3D electrons, a nickel 3D shell. And then you downfold with some Wannier-like technique to that subspace. Within that subspace, of course, proper interface to the rest, you do the DMFT calculation, always like one DMFT step, you get a self-energy out of this, and this you upfold again via this Wannier stuff, just the other way around, to the Hilbert space of the full problem, recalculate your Concham potential using the DMFT self-energy, and you get a new DFT step, and this whole thing, like a redshift, is then converged until everything, meaning Concham potential and DMFT self-energy are more or less converged. Yeah. So this is done. So there are some technicalities on this, which is not super important. We do QMC. It's charge self-consistent, so the charge is always updated in each step, so it's a full-fledged thing. We can do up to 200 atom unit cells, so we really can do material science with this. It's a heavy beast, of course. You have to do quantum Monte Carlo at each step. You have to use a supercomputer, but still, it's doable. Important what we do here, in addition to the standard DFT, DMFT scheme, we do an inclusion of correlations and oxygen, because I just said that for this Nickelates, we're in the regime of a charge transfer energy at the end of the row, which is still competing with Mount Hubbard physics. So we believe, for several reasons that we can also discuss afterwards, if interested, that correlations and oxygen are relevant. And we have seen this in other compounds like nickel oxide, rock salt. So we do this not with DMFT, but with some static-like scheme, not with DFT plus U, but with some self-interaction correction. We take out the nominal self-interaction that you get from DFT, and if you take that out, it somehow incorporates the effect of correlations in a better way, as it can be seen. And this has several advantages against DFT plus U. For instance, you get also band narrowing effects and so on and so forth. And you split the PD levels and all that. So this we do on oxygen, and it's incorporated on the pseudopotential level, which we use here. So it's iterated throughout the time. Further settings, of course, we have to choose a Hubbard U. We use 10 eV, and J, the Hund's coupling is 1 eV. We can discuss that also, why we use that, but let's take it for the moment that we think it's a good value because it gives good agreement for other systems. We have to take some parameter for this self-interaction correction. We have to take a double counting. So that looks a bit weird because it's not ab initio, and you would say, okay, you have a lot of settings that you have to use. But my take on this, yes, it is a bit like that, but that's just a complicated problem. And the important thing is that for all the calculations I'm showing you, for all different Nickelates, I use the same kind of settings. So I don't fiddle around with U's and J's, which you could do, but it's fixed for all calculations. And to get some reasonable physics out of the Korean picture, and this I think we achieve. Then we have to do a projection onto this correlated subspace, and there we use all the bands that we get from DFT, which are of nickel 3D and oxygen 2p kind of character. Okay, and let's discuss now a bit the physics that we get out of this. So what we see at stoichiometry for this neodymium nickel O2, we see that it's using this SIG DMFT, so with the self-interaction correction on oxygen and the full DMFT, we see that the system is very strongly correlated, meaning that the X minus Y square has already gone to the Hubbard bands, as we talked about. So there's it's like a mod insulating, an orbital selective mod insulating, but still these Z squares are there hybridized onto the self-doping bands. Remember here the DFT chart you can compare if you like. If we take out these correlations, the oxygen system is much weaker correlated, and the X minus Y square is still there in a not perfectly quasi-particle sense, but in a very blurry sense, but still there. And then, of course, the question, what of two regimes are the better ones? And okay, that is to be debated. But still, we believe that this is somehow the more tailored regime, and that the X minus Y square is really strongly mod insulating or close to be mod insulating, which is also in comparison to this very weak transport that we see in experiment. And we can compare this even to spectroscopy. So there's been angle integrated photoemission 2 years more or less after our prediction of the spectra. So this was for the praseodymium compound, which has very similar behavior to the neodymium. So one can take that as a comparison. So this was done from CX Shen's group, and you take this orange curve at stoichiometry. So this is the angle integrated spectrum. You see here this oxygen-like peak, and you have here the nickel 3D peak. And if we overlay this with our predicted curve, which is the red one, the matching is more or less close to be perfect. I just adjusted the height here. So again, the red curve is a prediction, and this is measured. Of course, the height here are the same because of the lack of matrix elements, but the peak positions are more or less fine. Whereas the standard DFT, DMFT, it's weaker correlated, so they have still kind of more weight at the Fermi level, is a bit off from that spectrum. I also have to say that very recent there has been RPES measurements that see some dispersion of X minus Y square in the second Brion zone, not in the first Brion zone, but it's very weak. So in our calculation, it's like a 0. So X minus Y square is fully mod insulated. Of course, measuring a 0 is difficult. We will likely measure maybe something, and that is seen here. there's a bigger discussion about this RPS data. It's very fresh RPS data, and it's again very complicated to measure all this. We can discuss it afterwards. And of course, there are now debates which is the right picture, but at the moment we still follow this one with this SIG incorporation, which to our belief gives the better physics also according to the charge transfer energy. So now let's go to doping. What happens with doping now? Well, we compare with the cuprate. So the picture is a bit complicated, but let's focus on the cuprate first. For the cuprate, we get this sunrise-like singlet. Yeah, so this, you see the oxygen peak is overlaying with the copper 3D peak just because of the small charge transfer energy, where they are still likely largely split here because of the larger charge transfer energy in the Nickelates. And you see the sunrise-like singlet in this inset is really composed more or less evenly of oxygen, which is here the greenish background, and this purplish, which is the copper 3D. So this is really sunrise-linked. Oxygen and transition metal oxide, transition metal atom go together hand in hand in forming the low energy quasi-particle peak here at overdoping. And then in the orbital resolution, it seems that X minus Y is the only dominant player at the Fermi level. Whereas when you go to Nickelate in the very same doping regime, you see that there's also quasi-particle peak, but now the oxygen content is much less, because the charge transfer is so high, it doesn't mix in easily. So oxygen is still there, but it's not a very strong sunrise physics because, again, the incorporation of oxygen is much reduced. And we see that for some reason, this nickel DZ square orbital, which is here also here pinkish drawn, is also mixing in the Fermi level. So it's really this two orbital picture at the Fermi level against the one orbital picture. So how does that come about? How does this nickel DZ square mix in? Well, the mechanism is now more or less clear. We cannot put holes easily on the oxygen because of this large charge transfer energy. So when you bring in holes, the system asks, okay, where can I accommodate these holes? In the cuprate, it's very clear. I will put it to oxygen because anyway, I can hop easily across oxygen from copper and so on to solve the small charge transfer energy. In Nickelates, that's not so easily possible because, again, the charge transfer is very high. So the system has to look for some other sink, so to say, for the holes, and the only one that is available, more or less freely, is this nickel DZ square orbital because it has no apical oxygen. It's more or less freely going to the rare earth sites, and it's at stoichiometry nearly filled, but it's very happy to catch some holes, because because of several reasons, and that also connected to correlations, and because of the fact that just the energy scale for putting holes in the X minus Y square is a very large energy scale. So what happens is that with doping, you pull up this original nickel DZ square band in DFT that is well below. It's pulled up to the Fermi level and forms this flattish band, and that is for us some reason for superconductivity in this system. Whereas when you don't have these correlations in oxygen, you don't see this, you will put the holes in the X minus Y square. But again, we believe that is a bit against the intuition of this high charge transfer energy. Okay, but of course the picture in detail is a bit complicated. It's not that one orbital rules it all and the other is completely irrelevant. Of course, it's a complicated issue. So when you bring up this nickel DZ square band to the Fermi level, you bring in also, as we can see, some coherency to the X minus Y square. It's very weakly seen here. It's better seen in the self energy here. That so the X minus Y square self energy becomes Fermi liquid-like more when just this nickel DZ square band comes up to the Fermi level. So there's a talking between these orbitals. So in the end, it could be that X minus Y square is still, of course, a key player for the superconductivity, but with the help of this nickel DZ square degree of freedom, as we think. Okay, this has been also seen in other systems. So we can now go to this result from Giulia Mandi, where she did now layers of this infinite layer type. When you see that you put in different layers, you can reach at stoichiometry for these different layers the same kind of doping reaching as doping the infinite layer with some holes. So if you put 5 layers of this lanthanum nickel O system with the apical oxygen absent, you get the same doping region as strontium doped infinite layer system. And we did also a calculation, and just to make this short, in our calculation, we also see again that this nickel DZ square band, which is here the pinkish character, is also again at the Fermi level, and the whole Fermi surface looks a bit strange. And the thing is that it's very incoherent, that the coherence scale is very small to reach. Yeah? Remember this coherence scale of quasi-particles that we talked about yesterday? It's very small here, so the very small temperature kills your quasi-particle very easily. This is maybe reminiscent of this also very fluctuating regime in an experiment concerning superconductivity. But again, photoemission still is lacking for these systems. Then very quickly, because I'm running out of time, as I see, so we can do then also minimal modeling of superconductivity, including these relevant 3 bands, the dz squared, the x minus y squared, and the self-doping band. So we do something simpler, not a full DMFT, but still we get the same picture, that we have a great attachment of holes in the nickel dz square once we dope. So all the holes, you see that filling is close to 2 at stoichiometry, but then all the holes go into that system. So you lose charge in nickel dz square, whereas the x minus y square more or less stays inert to that. And if we then crank up some regime for superconductivity, so we do a recoupling approach based on RPA spin fluctuations with Andreas Kreisel, and then we see that indeed in the interesting regime of larger correlation strength, that x minus y square is not the sovereign ruler anymore, but other instabilities come up, namely even a triplet instability or an S plus minus instability. So I don't have time to go in super detail here, but if you're interested more in these results, of course, we can discuss. So now for the very last few minutes, let's then also connect to these other systems, these 3D 8-ish systems here. And the first information from calculation is that if you do the nominal count of valencies again, then you would turn out that nickel is not 8, but 7.5. Yeah? And many people take this literally as 7.5. But of course, you always have to be careful. I mean, this is just a very simplistic analysis of oxidation states, yeah, from a very ionic picture. And that's not always true in a true system. So one has to be careful. It's the first guide, but it's not maybe the full truth in the very end. So what we do within the calculations, since I told you in the beginning, any oxidation state beyond 3D8 is very hard to reach for nickel. We also see in the calculation, again, it's 3D8. So there's a part of ligand hole on the oxygen again, which maybe is important for the physics. So ligand hole physics is not important here, but ligand hole physics is likely to be important here for this 327 and 4310 systems. So then the system can be at ambient pressure better characterized because it's a full bulk system. Of course, although the growing is still complicated, what they see is at the ambient system that there is already a transition to a spin density wave at around 100 to 150 K. And then the system is still metallic, but some kind of tricky magnetic order. They can also find the ordering wave vector, which is at the so-called X point, which is shown here in the photo emission. The X point is more or less here in between. And the question is, can we also find a reason from theory for this instability at the ambient phase still, which is maybe a competitor to superconductivity that turns out to be true at higher pressure. So when you do RPES on this system, which can be done, you see there's again a flat band. Yeah? Surprisingly, it's again nickel dz square character, but it's below the Fermi level at low temperature at 10 K measured. But the transition is at 100 to 150 K. So what we believe is that this flat band is, which is at the Fermi level from a DFT calculation for this system, is maybe split off from the Fermi level just because of this ordering transition, yeah, by some kind of generalized piles-like scenario. And we check this in the calculation, so we now do the calculation. There's another caveat, there are 2 different structural motifs for this 327 system. One, the canonical Middey bilayer structure, which is called 2222, and the 1313 structure, where we have alternating one layer and triple layer systems. Yeah? This is, sorry, but it's just so complicated. I cannot, can I say? No, that's what's found. And if you do the DMFT calculation, we see that it looks a bit Fermi liquid-like. So this is the self-energy in Matsubara space. So if it becomes linear at low frequency, it's supposed to be Fermi liquid-like, but it's not. Even it looks like a bit. If you analyze it concretely, it's not super Fermi liquid-like. Whereas here it's even more dramatic. So here you even have a multi-insulating regime because of a very high self-energy for the monolayer part, which is reminiscent of this 214, which is a monolayer, which is mod insulating as we saw in the beginning. Whereas the tri-layer segment is still metallic. Now, if you do the full DMFT calculations on this, so what we see again that this nickel dz square flattish band is pushed to the Fermi level at temperatures above this transition. And what we then see, if we do the calculation of the susceptibility, that indeed we have peaks at these X points, no, for both structures. And this tells us that indeed this nickel dz square flattish band, which is there at the Fermi level at higher temperature, drives this spin density wave transition at ambient pressure and is then likely split off in the ordered phase. We cannot compute the ordered phase very simple because the ordered pattern is intertwined between charge and spin order, and it's a bit hard to reach, and it's still on the table what is the definite structure. So we can only nicely compute and well-defined compute the system above the transition to spin density wave. But still we get the good nesting vector and the good instability. Now let's finally go, of course, to the, I need 1 or 2 minutes, sorry, but then I'm very quickly finished. So let's go to the high pressure regime. Then, of course, things become a bit even more striking, because now you have this flat band at the Fermi level, which is not split off, because with the high pressure, you suppress this transition to spin density wave. And then you have a very intriguing Fermi surface here, very flattish band from the nickel dz square intertwining with X minus Y square. It's very non-Fermi liquid-like. Yeah, you see this by this downturn of the self-energy. Also for this other structure motif at high pressure, same thing. But even more interestingly, in that part, we see the formation then of these kind of Fermi arcs, which are reminiscent of physics of cuprates. Now, in cuprates, these Fermi arcs come from a nodal anti-nodal dichotomy, whereas here it's the same kind of thing, but it's not from a non-local physics. It's just that this flat band destroys the coherence in the antinodal part, whereas it still survives the flat band strong fluctuations in the nodal part. So it's a multi-orbital feature that here gives rise to this Fermi arc-like scenario. But still, it's maybe interesting that you can connect then to cuprates in this level. So how this can we now, this is the very last slide, so how can we now connect these two different systems, so the 3D 9-ish system and the 3D 8-ish system? Well, just by this band and different doping regimes, that at least is our thinking, that you say, well, in this 3D 9-ish system, I have a flat band on top, yeah, that blend here, and you dope into this, and you reach superconductivity. In the 327 system, the same band is still there. Of course, it's a bit folded to a different structure, but now you have a different occupation. You dope then into this lower branch of this flat band, which you can see here, which is then filled with 1 electron, whereas here it's nearly filled. So you always have these kind of flat band parts of the nickel dz square that seemingly is always somewhere there, close to superconductivity, and we believe that this is a common player that maybe connects those two different superconducting nickelates. That is my conclusion slide, and I'm over time already, so thank you for your attention.
Thank you for the very nice overview. And the talk is now, yeah, Silke.
Right.
Everything, or only to the oxygen sites?
Only to the oxygen sites, to the oxygen orbital, to oxygen 2s and 2p.
How do you then get around the double counting? Because in principle, you still have the question of what you add for correlation. Oh, sorry. Thank you. So you still have the question of what you add for the correlations on the D side, and the relative energetic position between D and P should rather become worsely defined than before. So I'm not sure I understand your remark on the double counting in that context. I mean, I like the method, and it obviously looks very nice. It reminds me a bit of what we have been trying with Green exchange plus the MFT and corrections of hybrids and things like this. But for the double counting, I'm not sure I understand completely.
Well, of course, there would be a bigger discussion to the double. So what we do is, at the moment, very simplistic. So our argument is that in some sense, the strong correlation comes really from the DMFT, but the large scale is the U. The SIG is a smaller refinement. If you also compare the SIG calculation to the DFT calculations purely only, Without DMFT, there's a very small refinement, so to say, in the overall structure. So we say that strong correlation comes from the DMFT part, which is happening on nickel, which is disconnected from the oxygen, at least in an approximation. So we only apply the double counting correction to the nickel side. Of course, you can agree, you could say might be still some subtle double counting issue between these two sectors, which is beyond our simplistic approximation. Might be, but then of course things become very tricky how to do that in very detail. And at the present level of investigation, our statement is there might be subtle differences, but they are not so super important for the qualitative issue. The qualitative issue here is, can we do an enlarged PD splitting? And we reached a large PD splitting with that, which we know it's too small always in standard DMFT. So we can now say, is this an enlarged PD splitting, which is improving and better compared to experiment? Is this still the perfect corrected one? Most likely not, but it's better than the standard one. Are we in this more strongly correlated regime for the X minus Y square, or are we in this weakly correlated regime? I fully agree that at the very end, there should be more discussions, but we all know that all these hybrid schemes, that's very complicated in terms of double counting. So, but at the moment, we try to keep things simple and do not introduce a kind of additional double counting that is connected directly to the SIG. But I agree that at some point that should have been thought over a bit more in detail. Yeah. Yeah. Well, but okay, but you see this I don't have the plot here, but it's published in some other work. But you see the effect of the self-interaction is to localize the oxygen 2p. That is very clearly seen. So if you plot a charge density, you can even see that you compute a new kind of Coulomb potential, R-dependent with the SIG. And you see there it's a bit lower in some certain distance from oxygen, meaning that you more localize oxygen 2p in some range. This is just the effect. Well, effectively, sorry. But effectively, of course, since the SIG is introduced on a pseudopotential level, so it's not put in statically once and for all, it's like a potential. So it's iterated throughout the calculation. Therefore, it of course also renormalizes the UPT. So we have not tried yet to somehow fetch out the UPD in the two different schemes, but it could be done by some means of well, you would export on this on some kind of annualization or RPA-like fashion. So that could be dragged out, and I would be very clear, would be strongly thinking that UPD would be larger than with the SIG. So it's, of course, the UPD is not directly implemented, but since the oxygen is more localized and somehow is a bit more stubborn concerned to charge transfer, I think the UPD would be larger from that kind of calculation.
Yeah. So I would like to make a question about the ligand hole that you spoke about. So in this high pressure Nickelates, right, has been found a ligand hole. So the question is the symmetry of the ligand hole, let's say, different from in plane? And yes or no?
That's a good question. Yeah, that's a very good question, in fact, yes. We have not analyzed this completely yet. When we did the calculation, it's still on my list, so to say, it's more or less there, but I still didn't do it. So I just, when I presented these numbers also in the first slide, I just integrate over all oxygen states. But of course, you could selectively integrate over different ones. And you see that in the band structure, there's a specifically this oxygen, which is the one that's connecting these two bilayer individual layers, is having a stronger kind of mixing in closer to Fermi level. So I think there's experimental data on this. This was also a Nature article some weeks ago, yes, that they say that there is some anisotropy, as you suggest, in this ligand hole. And I think it's in the calculation, but I have to drag it out.
I would like to add a comment, because in the cuprates, there has been for very long, since you spoke about analogies, etc., in the cuprates has been a very long time considered the materials as a single band, and the Zangrai physics basically dominant. Now in these materials you show that Zangrai's physics is not so important, at least for the and in cuprates there were experimental evidence in the early stage, I mean the early age, like in the 90s, 80s, actually late 80s, 90s, where X-ray spectroscopy show that you have a ligand hole, right, with a different symmetry, respect the in-plane symmetry of the CO plane. And this led to the idea that you have a two-band system to describe the physics of the cuprate. Now, for let's say 30 years, people keep modeling cuprates with a single band. But now what you're showing is that when you apply a pressure and you get to the physics close to the one of the HIPCO, because you have the temperature scale, the ligand hole becomes important and you have again a second band system. So I think this is really showing that you have something to think about. I can mention also the works that show this ligand hole in the cuprates, but they were most of the time completely neglected in favor of this Zangrai physics that in these Nickelates is not important anymore.
No, I completely agree on you. I mean, I was very short-lived on this one-band stuff, but I also believe that the one-band is too limited for cuprates. There have been new works also, you know, guys like Seamus Davis, that's also super exchange now, scaling and stuff. So people are now waking up again a bit on oxygen degrees of freedom, and also this kind of feature that we find that there are 2 degrees of freedom that governs the physics in the Nickelates. It's also telling me something that maybe you have to think in similar terms about cuprates, where we always thought it's purely non-local physics that lives in one band, which is maybe true, but you can maybe rephrase the problem differently, that it's also maybe a hidden kind of degree of freedom in the cuprates, which is more or less carried over by Nickelates, by the flat band, so to say, which is somewhere still there in the cuprates, which you have not identified yet. No, you maybe also know there are these hidden fermion theories by people like Fujimori or something. That there is something which we have not yet identified. It could be also connected to your picture of this ligand hole, but there's some degree of freedom in the which is beyond the one band, which you have not yet identified. I think on that we agree on cuprates.
So thank you again, and in the interest of time, let's move on.
Thank you.